Section 4.6, rank. Rank is a very simple idea. We have just talked about the dimension of a column space, and the dimension is the number of vectors that form the basis of a column space. Well, it turns out rank is just taking one of those dimensions and applying it and giving it this new name. Specifically, the dimension of a column space is what you have. That's what the rank is. The nullity of a matrix is the dimension of the null space. Now, our book doesn't use that term nullity. I've seen it in other books, so I just wanted you to be aware of it. You're going to continue to hear it just being asked, what's the dimension of a null space? But again, the dimension of a column space is this new thing called the rank of a matrix. So let's start with a problem and call out some subspaces. You're gonna learn about a new one today, but we're going to identify dimensions and ranks. So I've got this matrix A, and I've row reduced it only to the point of echelon form. So let's call out what we know about this matrix right now. One of the big subspaces is the column space. So let's call out the column space of A. How do I do it? I can't see it here, but this is where my columns are. It's in the reduced form that reveals where my pivots or my basic variables are. So I see one in column 1, my next is in column 3, and the last one's in column 5. So that tells me where to find my column vectors in my original matrix. So here we go. We've got the first column, the third, and the last. So the set of those vectors form a basis for the column space of A. So other things we could say then, the dimension of the column space of A, which we've already talked about, is 3. But that tells me the rank of matrix A is also 3. There's the new thing. Here's a subspace we haven't talked about before, but we're going to start bringing into the mix, and it's the row space of a matrix. Now, like the column space, my row space is not identifiable in the original matrix. You have to row reduce it to echelon form. But this time, my vectors as rows are taken from the echelon form. And the reason is, you might think, well, how about my first 3 rows? Since those are where my pivots are, wouldn't it just be the first 3 rows in matrix A? The reason we can't say that is we're not sure if there was a row swap in the process of creating this echelon form. Notice we've got an entire row of zeros. We're not sure if that was the original bottom row. So to get my row space, first of all, I like to write it as a row. Every row that has a pivot is that vector. And so I'm going to write it in the old-fashioned ordered in tuple. So 5 elements. And I like writing it as a row only because it reminds me of what type of vector it is. But don't be fooled. These are vectors in R5. And when you get your online homework, you're not going to be entering them like rows. You're going to be entering vectors like you always do, as columns. So it might seem weird to write a row space as 3 column vectors, but it doesn't matter. So there we go. What do I have here? I've got the dimension of my column space, my row space is also 3. And I don't need to call it the rank because the rank has everything to do with the column space, but it turns out, even after this one example, it's not a surprise that the dimension of the column space and the dimension of the row space are always going to be the same because it has to do with the number of pivots. And once you've identified 3 pivots, that tells you there's 3 column vectors and there's 3 row vectors that work. The difference, though, is notice my column space is a subspace of R4, where my row space is a subspace of R5. Well, so there's your new subspace. We've got column, row. Let's revisit the third subspace that we've already identified, and that's the null. And this is the one where you do have to take it all the way to the reduced echelon form. And we can see here there are 5 variables. I see two free variables, so x2 and x4. And here come my other 3 basic variables. Here's my x5, looks like it equals 0. x3, positive 3 halves, x4, and my x1 is 3x2s minus 5x4s. So we unpack that with an x2 sitting out in front, 3, 1, 0, 0, 0, plus x4, negative 5, 0, 3 halves, 1 and 0. So if you're asked for the null space, again, these 2 vectors qualify. I do want to offer an alternative to this one. So the null space of A is the set that contains these 2 vectors. Actually, it's the span of these 2. So I like the first one as is. Again, the second one is fine. In fact, if you enter it in your online homework, it will take it. I kind of prefer my vectors to look a little cleaner. Let's get these all integers. So if I scale this by 2, that's perfectly okay. So call that negative 10, 0, 3, 2, 0. That's my preference, but again, not required. So what do we know? That is the dimension of the null space of A is 2. It's the number of vectors. Well, one final note I'll squeeze into this corner. It turns out then, once you've identified a matrix and its pivots, you have everything you need. Let me point out then, let me squeeze this in back up here, is that if you take the number of basic variables and add that to the number of free variables in an m by n matrix, that is the number of columns, or n. Well, the number of basic variables, that is the dimension of your column space, or your rank. And the number of free variables is the dimension of your null space, or the nullity. So those all come together. So identifying your variables is a key feature of your 3 subspaces. Column and row both always have the same dimension, which is the number of basic variables, and the dimension of your null space is always the number of free variables. Let's look at another set of problems here. So I'm going to give you a generic setup. Let's imagine a 4 by 9 matrix, and we're told it has rank 4. This isn't always necessary, but it is occasionally nice to just visualize, oh right, 4 by 9, it kind of helps to put little dots there. And I'm going to ask you a series of questions related to this. The fact that we know it has rank 4, what does that tell me about my matrix? Well, rank has everything to do with the dimension of the column space. And if the dimension of the column space is 4, that tells me there are 4 basic variables or 4 pivots. Doesn't matter which ones, but it might help to circle some just 4 on the way down. How about in the first, the third, whatever that column is, and how about the very last one? Okay, so that's what it could look like. So let's answer a series of quick questions. So what's the dimension of my column space? Would be the number of those basic variables, as 4. Then what's the dimension of my null space? Well, that's the leftover columns. So it looks like there's 9 columns, 4 of which had basic variables. That leaves 5 free variables. There's your dimension of null space. So what would be the dimension of your row space? I see 4 pivots, whether they're in columns or rows, so that's also 4. So what is the rank of this matrix? It's the dimension of the column space. What is the nullity of this? That's the dimension of the null space. And every once in a while, your online homework might throw in something like this. What would be the rank of the transpose of that matrix? It would then be a 9 by 4. Well, I think those pivots would still be there. And so I don't think the rank changes, even if we transpose a matrix. It remains 4. So let me ask you last two questions about this. What would be the span of the column space? Let's say if I could span all of those column space, would that equal all of our 4? And it looks like it would. It looks like I would need 4 vectors that are independent or have 4 pivots, and I got it. So there's my answer. The dimension of my null space is, we said was 5, so is the span of the null space all of R5? Well, that doesn't even make sense. The answer is no, first of all. But remember, the null space is what subspace is it, or what vector space is it a subset of? Well, the null space is a subset of R9. And so this question doesn't make sense. So but I did want to make a connection. Does the dimension tell you what R space it covers? Not necessarily. All right, let's try another one. A 5 by 2 matrix, we're told has rank 2. So again, here's a visual. So we could say, oh, there was a pivot here, or maybe one here. So what does that tell me? The dimension of my column space, we got it. The dimension of the null space, well, there's nothing left. There are no basic variables, so that is true. The null space can't have a dimension of 0. Again, my row space, same as my column. All right. I won't draw a matrix out. You might find it helpful, but let's move forward. If you're told a 4 by 5 matrix has 3 pivot columns, what can you tell me about the dimension of the null space? Well, if it has 3 pivots and there were 5 columns to start with, that leaves the last 2 not having pivots, and there's the dimension of your null space. Would my columns in a 4 by 5 span all of R4? Not with 3 pivots. I would have to have 4 pivots for that to be pulled off. Answer, no. Last one on this page. If you're told the null space of a 5 by 7 matrix is 4-dimensional, what's the dimension of the column space? Again, we always focus on the number of columns. So starting with 7, if we're told the dimension of the null space is 4, that leaves 3 leftover columns that have pivots. And we got it. All right, one last set of ideas. You will remember in chapter 2, the invertible matrix theorem, the biggest theorem that we cover in this class. And hopefully you still have this sheet, or you can refer back to the invertible matrix theorem. All these statements, starting with any square matrix, if one of them's true, they're all true. If one of them's false, they're all false. Notice where this left off. I mentioned back in the day that this theorem never ends, though it did stop at letter L. And so I've got a continuation of the invertible matrix theorem. Just a few statements for us to consider. So let's say, so M through R, if we have, again, the setup is, let a matrix be an n by n square invertible matrix. What can you tell me about these statements? Well, if it's invertible, what do we know about this matrix? The columns of A then form a basis of Rn. What is the column space of A? Again, what that's asking is if you could span all of those columns. Yep, they would span all of Rn. What is the dimension of the column space? Well, it looks like every column has a pivot, so it looks like the dimension is all of n. Then what would be the rank of A? Well, the rank is the same as the dimension of the column space, so also n. What is the null space of A? Well, if every column has a pivot, there's no basic variables, then the only solution to the homogeneous system would be the trivial solution, so there's at least one thing in the null space of A, and it's just the zero vector. And then what's the dimension of the set of vectors that contains only the zero vector? It doesn't even have a dimension other than 0.